Okay, good morning, everyone. Welcome to Scheme Workshop. We're going to start off with Andy talking about Scheme on WebAssembly. And I'll just say, to make sure all the questions in the talk get the audio gets recorded nicely for the video, please speak directly into the mic. So when we take questions after, I'll pass it all around. Okay, but let's take it away, Andy.
Good morning, and thanks for coming here at the first talk of the day on the last day of the conference. I know everyone's a little bit tired. Good to see everyone. Today, I'd like to go through and talk a little bit about, first of all, as schemers, where can we run scheme programs, and what's the sort of missing piece, to my mind. And then missing piece is obviously WebAssembly, because that's the talk. And then we talk a little bit about what kind of WebAssembly we need to produce to run Scheme. And then finally, we do a sort of deep dive on the scheme that I've been working on for the last year and a half, 2 years or so, called Hoot, which is Guile for WebAssembly, with the scenic detour, because we have an hour. So, all right. So first of all, let's think about Scheme in 2024. You know, where are the places that people can run programs, right? It used to be that everybody just ran programs on their computers, like native binaries and such, and Scheme, you know, as an old language, targeted this use case quite a bit. But it's waning as a way to run programs. It still exists, but it's not the totality of computation anymore. Maybe 20 years ago or so, we started to have users accessing programs over web browsers, and the programs ran on servers with HTTP as an intermediation. And on the internet, you know, nobody knows you're a Scheme. Okay, fine, we've got web servers. In browsers, well, people these days run a lot of computation in their browser itself, and their JavaScript is really the king. So it's not really a Scheme land, such as it is. And then finally, we have on servers with Dockers and Kubernetes and things like this. And I'm glad this is other people's problems. It's not mine. So let's look a little bit more closely at what I think is the sort of main missing piece for Scheme in 2024, which is on the browser. Browsers are pretty weird computational environments in the sense that every time you visit a web page, you install a program. And the web browser has to see the program as new each time. It can't cache very much. Even for an application like Gmail or something like this, the actual code changes so many times a day that as you use the program, like going and visiting it a second time doesn't necessarily mean you get the same code as the first time. And that's besides the question of JavaScript on ads or tracking third-party scripts and things like this. Also, as a computational substrate, I know many of us in this room have powerful Androids and iPhones, but that's not actually the majority of the world. There's a lot of low-power devices out there on which programs are running. And so this leads to a very hard constraint as to how much code you can actually ship over the wire. You're incentivized to make very small bits of code. And in the same sense, the network is good in some places and not good in others. And this also imposes a constraint. You can't ship 10 megabytes. Well, maybe you can, but that doesn't lead to a good user experience. And then finally, if you're going to ship a program, you have to ship it in a form that can run, and the form that can run on the browser is JavaScript, meaning JavaScript source code. You have to compile and produce JavaScript source code, which is a thing you can do. And so if you think about, let's target Scheme to JavaScript, this exists, it's out there, and on the plus side, the JS virtual machines are amazing, right? I did a back-of-the-envelope calculation the other day, and I think like JavaScript VMs have gotten at least $1 billion of engineering investment in them. And where else are you going to get this for free? The other wild thing about them is that they are like constantly resourced, and then the people that run JavaScript, their browser is actually updating all the time. So you have access to new standards in an ongoing way. It's a maintained system, and it's everywhere. So it's a good substrate from that sense. But just because you can target JavaScript doesn't mean that necessarily it's a great idea. If it's your only option, yeah, certainly. But as far as the qualities of a compile target goes, it has a number of drawbacks. One, when you compile something, you want to compile to primitives that have known semantics. This is hard on JavaScript because the user can redefine the meaning of math.sign, right, during runtime. There are workarounds to this as to many of these other things, but it's unsatisfying. Also, because of the way that JavaScript engines work, there's a lot of randomness to the performance. You measure performance one time, it's not necessarily going to be the same thing as as running it a second time just due to when things get inlined and compiled. And a small change might result in a large change to performance because maybe you get the good inlining path versus not the good inlining path and things like this. The numerics are floating point numbers, essentially. There are big ints now, but it's less performant. There's no tail calls, which makes it a pretty hard compilation environment, unless you do trampolines, which, I mean, it's kind of gross. If you want to recurse to your heart's content, if you want to write the usual recursive map, you can't. You're limited in terms of the size of the list you can map on by the size of the JavaScript stack. That's pretty unsatisfactory. It's single-threaded, and I mean, as a compilation target, emitting source is unpleasant, right? But if it's the only thing out there, it's what you do. And so C++ world started doing this about 10 years ago with a modified version of LLVM, which emitted JavaScript, but in a very tight dialect of JavaScript that could be statically typed and guaranteed to compile down to some primitive operations. This it was a good proof of concept, but I think people were disgusted enough that we made WebAssembly afterwards to more formally codify this practice, which made WebAssembly essentially at that time a machine for running C++ programs and Rust programs now, but not Scheme programs, because garbage collection, while always planned, wasn't included in the beginning for, you know, path dependency reasons. So now, though, that this is the new opportunity which is afforded to us. GC is now available, right? Since the end of last year, it landed in Chrome and Firefox. It's now in Safari Technology Preview, so it will be out in Safari on your iPhones and iPads or whatever very soon. And so that means it's time to make some WebAssembly. It's time to ship some programs to the user in the form of WebAssembly or GC. So in the rest of this talk, I'm going to look at what the machine gives us and what kinds of code our scheme needs to map to. And then we're going to look structurally as to how the Hoot compiler is built. So when we look at the primitives afforded to us by the WebAssembly GC proposal, there is a type tree. It's a type system. There are 3 top types for historical reasons. We mostly deal in the any type tree. So there's a subtype, there's a subtype of any called ec. These are those values which are comparable by equality. And then subtypes of ec are I31, which are fixed nums. There's structs, very low-level GC managed data type with user-defined fields, and arrays, right? And off of this, we can build our structures. In Scheme, you know, as we know, it's a unitype language, if you will. Maybe you can sometimes infer some properties about data types, but generally speaking, you have a universal data representation. And we're going to choose ref ec, which is the type which is comparable by equality, because we need ec in Scheme. And within the ref I31 space, you can either use it all for fixed nums, or you could take half of it and use it for other immediates, like characters or booleans. This is what we do in Hoot. And then finally, as an interesting observation, all these types are nullable or not. You specify them. In Scheme, we don't need a null type, so we'll just go with ref ec, precluding null. And then when we look at how do we represent objects, in Scheme, there's very little type generativity, right? When you define record types and when you define closures, these are when you actually generate new types. But otherwise, in a Scheme system, you'll have, you know, your 20 or 30 types or so for which you need to represent. And in WebAssembly, what you can do is, so first of all, it's got an odd typing discipline. It's called iso-recursive types, meaning that generally types are structurally comparable. So if you define a struct with the same type fields in one module and the struct with the same type fields in another module, those will actually have the same type, right? You can do dynamic checking as to what type of value has, but given that those 2 types in those 2 modules are the same, like you might get some type confusion, essentially. However, WebAssembly gives you this kind of escape clause, which is the recursive type group. You explicitly say what sets of types can reference each other recursively, and then within that rec group, you have essentially nominal typing. If you have the identical rec group in another module then you can have type confusion. But it's pretty unlikely to be the case. So this is the general strategy. So for example, we might define a supertype for heap objects. We don't have hash codes, right? So if you need to hash values, if you need to actually get a hash code from a value, then you need to have it on your objects. So we actually define a supertype for this precise reason, to be able to attach a hash equality value to all objects. And every subtype then has to mention that hash field as its first field. It's an I32 in this case. And then we have our pair type, which has a car and a cdr. Right? It's pretty straightforward here. Then how do we work with these types? So first start would be to define a const function. Now, in WebAssembly, all the functions are typed, meaning in terms of arity and types of parameters and types of results. So let's say we have a const which has two parameters, the car and the cdr. The labels are optional in WebAssembly. And what I'm showing you is the S expression or textual representation of WebAssembly code. The textual representation has a direct, unique correspondence with the binary encoding. One binary encoding can have a number of textual representations, but what is this, like injective or one of these words, right? So, and the names go away. They turn into indices. So we have two parameters, the car and the cdr, and to pack them up into a pair, we do struct.new, referencing the car and the cdr. And then I put a 0 for the hash field, because in Hoot, we lazily initialize these whenever we actually ask for a hash code. And then to get the car out, then if you have your pair as a parameter, then you directly get struct.get pair car, and this is all requires no type checks at runtime. Everything is wonderful, and then you return your result. However, in Scheme, you generally don't have like a pair type coming in. You generally have the unitype coming in. You might not, but you know, in the general case, this is what you have. So you have to do a type check. So what the WebAssembly has a number of primitives for doing type checking. This one is probably the best. It's you try to cast this value from a ref ec, from the unitype, to the specific type, the ref pair, and if it fails to cast, then we're going to jump to this other label with the value with its original type, with ref ec. Right? So that means that this block here, in WebAssembly, it has structured control flow, and the only targets of branches can be blocks and the various kinds of blocks, block, loop, try, and if, right? And when you branch to a block, you actually branch to the end of the block. And so that value flows in on the stack, and then flows in. It can be a parameter to type error, for which we don't specify the type here. And then the control flow does not continue, so we don't have to actually provide a ref ec to return to the function, right? But what this means is that we end up doing a tail call, return call, to car, our specific function, with the specific type. So this is our dynamic type check. However, Scheme is special in so many ways, right? And one of them is that we don't have type checking on functions. We don't know how many arguments they accept in general, nor their types. So if you go to code up a function like list or something like this, what is your type signature here? Well, WebAssembly does not give you a primitive for this. Really, you would like this to be supported directly in WebAssembly, to have some sort of varargs facility, but that's not what we have. And so what are we going to do? Well, it's gross, but we have to virtualize the calling convention, right? In the case of Hoot, well, in any case, we have to pass somehow the number of arguments to the callee, which many Scheme systems do. And then let's pass the first few arguments in fixed locations, which probably get register allocated. Okay, great. And then if we have any more, right, because we can't have any number, let's put them somewhere. Hoot puts them somewhere else, but here for simplicity, and this might even be a better idea, we'll put them in an array, a heap allocated array, which might be null. So if you pass up to 3 arguments, no allocation, more than 3 arguments, some allocation. It's kind of gross, but that's where we are. At least we have the ability to do var args. Okay. So the code might look like this. Like you might have to actually insert a check for var args and check that the number of arguments is 2 because you have not only the pair, but you have the closure being passed in. And if it's not 2, then you jump to your bad arity, which will call wrong number of arguments and perform an exception somehow. We're assuming the existence of some sort of stack and exception handling somehow here, right? And otherwise, we return call to car, which will then do the type checking on the value you see, and eventually returning the result. However, in Scheme, we also have multiple return values, right? And so we don't have any static ability to know that a continuation accepts 1 value or 0 values or n values or any number of values. So what do we need to do here? Well, one idea would be to just, for the unit type of functions, maybe we would give the same treatment to the results as we do to the arguments, because WebAssembly can have multiple results. So maybe you return an n-args, and an arg0, and an arg1, as results. And this is getting a little bit silly, and it goes to illustrate that if you have a dynamic language and you're implementing it on top of a static system, you have some necessary overhead. And ideally, the spec will adjust to natively accommodate this overhead in such a way that doesn't impose overhead on the kinds of languages that Scheme is, right? So have var args, for example. That would be a nice thing to have. But we can get back to it a little bit later. Another question would be prompts, delimited continuations. Guile has these. They're pretty important to us. They're the basis for Guile's native implementation of exceptions and fibers, lightweight threading. And we want these, right? I'm not really willing to compromise on these. And if I have to compromise on this, then I'm going to give up, because I don't care, essentially. So our approach in Hoot, and one approach is to do a CPS conversion. And that makes stacks explicit, and then that makes the limited continuations explicit slices of stacks. There's some details involved in this. You essentially stack allocate return continuations. This is pretty classic CPS conversion stuff. Before you do a call, you push your live out variables, which is a flow analysis problem, and those might be typed. And then when you return, the callee will then pop those live in variables from the stack. So you have a kind of stack allocation discipline for return continuations. And then prompts almost fall out of this naturally. I mean, there's some, neat little details, but it's no essential cost beyond the cost of CPS converting your program, which is a cost. But the good thing is that there is a proposal in the works to add native effect handlers, which is delimited continuations, to WebAssembly. I would love to use this. My only reservation is that I don't want a limited stack, right? I want to be able to write recursive map, essentially. I don't want to have to accumulate in reverse or something like this. And JavaScript implementations have historically had a pretty limited stack for JavaScript code execution. Those are the ones I'm targeting. Probably they're going to impose a limit on Wasm stacks. But maybe with effect handlers, browsers are going to be obliged to implement expandable stacks, and maybe they'll give a big stack limit, like they won't limit it so much. I'm not so hopeful. But then I thought, and this is a side thought, that maybe I can use effect handlers to implement expandable stacks. That Stack Overflow could itself be an effect. I could capture a continuation, bounce back to the beginning, and then start again. It wouldn't be optimal, but it would, for a large stack, but it would probably improve performance for anything that doesn't blow the stack. Just a thought. Happy to talk about that later. Okay, so that's the code we need to emit. Now we need to get there, right? Like what kind of compiler do we need to write to actually produce this code that we would like to see? So I co-maintain Guile and have for the last, 12 years or something, 15, I don't know. Time flies. And Hoot is essentially Guile the language, compiled to WebAssembly. And we want it to be exactly and precisely Guile compiled to WebAssembly, because who wants to make a new dialect of Scheme? I mean, for research, sure, but you want to bring your programs and bring your your programming community, which is probably the more important thing to make sure that something survives over time. However, there are some deployment differences, whereas Guile is essentially a dynamically linked scheme with a separate compilation of a bunch of modules with some cross-module inlining. For the browser context, we need to ship one binary, and we need that binary to be very small. We need to only include the functionality that is in the user's program. We need to do maximal tree shaking on that binary. So it involves a kind of different construction for the compiler itself. We reuse the front end and the middle end of Guile, and then we have a new back end, essentially, is our strategy. And all this work is supported by Sprightly Institute. We'll get to see it in just a minute. And our goal is to get the Sprightly's Goblins project, which is a distributed OCAP system, onto the web. Now I have a demo. Hey, let's look at this. This is a game called, I don't know how to pronounce it. Is it Circoban or Chircoban or Kirkoban? I don't know. Chircoban. Okay, Chircoban. This is written in WebAssembly using Guile and Hoot, and it's a lovely little game. I don't actually play very many games, so I don't know very much about it. It has an embedded like wire world environment, so you have to sort of build circuits as levels get higher and higher. It's really fun. It works in Firefox and Chrome, obviously, because those are the ones with Wasm, GC, and tail calls. And it will work at some point in Safari, so we're getting there. But don't load it up on your iPhones right now. You might be able to load it on your Androids. So I mean to say, this is a real thing. It exists and produces code. There's a single binary. It embeds all the sprites in the binary itself as usual. It's this whole program compiler, right? And as you can see, Wasm GC has access to host primitives. You can define essentially an FFI to import things from the browser. I'm sure that folks that have been compiling Scheme2JS for a long time will recognize all of this. Canvas demo is the classic Scheme2Browser demo. Have fun, have fun. It's real good fun. But let's talk about the compiler, because I used to play games, but now I write compilers, because compilers are the game, right? So the basic structure is on the front end, we have a library group implementation. This is Andy Keep's work from 10 or 12 years ago, that essentially takes your set of modules and packs them into a big letrec star. And then we let the front end chew on this a bit. The partial evaluator will include only the things that are needed on the high level, and also do some inlining and code folding and things like this, which is also the Waddell DibVig online partial evaluator. And then, let's see. And the fixed letrec actually breaks that big letrec star into a bunch of nested fixes, fix point for functions, and then let and set. I have a little article about this. Now, the library group is a funny thing. And whole program compilation of Scheme is a funny thing. It's unlike any other language I've ever really worked on. This is a graph of the modules that this is part of the runtime library of Hoot. We've had to import and adapt some modules and then write a lot of modules fresh, because Guile, as an implementation, has a big standard library, and a lot of it is written in C or lies on C somehow. We need to bootstrap in a different way, so we've had to write a bunch of other things. Now, this graph has levels in which each level uses modules from the level below, right? Or at least from the level below. And in Scheme, and you're probably all aware of this, like each module defines like syntax which other modules that import it can use. This is a phasing problem. Guile has historically not done phasing very well. But what it means is that a module at the lower level needs to, and these are all expanded on the host in Guile, needs to have those macros present on the host in Guile so that the next level can actually use them, right? So there's a kind of liveness. The modules are live on the host so that they can be used to expand other modules that are being compiled for the target. But what's more is those syntax, the syntax transformers can use first order bindings also from imported modules. And so it's not just the macros that you need to have, which you would only need the macros if you just had like syntax rules, but with procedural macros, you need to also have the first order bindings. And so it means that you're sometimes when you're implementing a primitive that needs to run one way on the target and another way on the host, you have to do some cond expand work to provide a definition of it that works on the host, and also another definition of it that will work on the target. Even if this facility isn't used by macros necessarily. And for example, the record type system works this way. It has some procedural aspects, and those procedural aspects need to be defined in such a way that they can run on the host and on the target. There are some details here, and I'm happy to talk about it. But I want to get to a scenic detour. When I saw that I had an hour here, then I realized, you know, I want to push some ideas in the world. So I want to talk about the middle end a little bit. So we've gotten to the front end, and we've talked about the kind of code we want to produce. So we have the middle end and the back end still to talk about. The middle end is mostly still Guile, but I've never given a presentation on this before. So I wanted to push this thing out. So compiler middle ends. Forget what you know about Scheme. Think about like you're in like a compiler class, or the first time you learn about, you know, intermediate representations. The goal is to bridge the gap between your front end that has an AST and the back end, which is, you know, machine code and goto and things like this. Like that is the purpose of the middle end of a compiler. And you need a language which is fit for purpose, which allows you to make this link from front end to back end. So if you have a program that's like adding 1 to either 42 or 69, then you're going to get maybe a comparison of, you know, x to false. And if it's false, you take one branch, and if it's true, you take the other branch. And what kind of language can help us bridge this gap between the algebraic and the imperative? And the classic answer, of course, is a control flow graph, right? You have basic blocks. You have goto, essentially. Your program is represented as a graph. Your graph is an array of blocks. And each block has predecessors, successors, and instructions in it. And in the 70s, the instructions were control instructions like goto, but also assignments, not variable definitions, assignments to locations. And so in our example, we could have basic block 0, in which we branch on the value of x to either BB1 or BB2. And then in BB1, we would assign 42 into the location denoted by T, and then go to BB3 at the very end. But the other branch would be to assign 69 to the same location denoted by T. You have one location and 2 assignments in your program. And then finally, you add 1 to the value of that location and then return it. Assignment, not definition. Hard to work with, as we all know. I don't know if you've followed the history here. In the 80s, people rediscovered that functional programming was a great idea, that we shouldn't be mutating locations when we're trying to understand programs. And if the whole job of the middle end is to understand your programs, you should define rather than assign. And that's what static single assignment is. A location is only assigned once in a program, and that is a property that you can know statically. So your program is still a graph. Your graph is an array of blocks. Your blocks have predecessors, successors, and then these phis and instructions. And a phi is this funny function here. Your instructions are the same functions. But the novelty here is that on these 2 branches of the if, we're defining different variables. And then when we come to the control flow join, we say v2 is going to be, you know, either v0 or v1, right? And phi, as most people know, it's kind of a backronym in a way. When they originally published this, they're like, this is a phony function, but I'm not going to get my paper accepted if I label it phony function, so I'm going to call it phi. And I think, as far as I understand, that is the actual truth there. So SSA, standard, everybody uses it now. But there are some refinements, especially in the functional world. Milton did, I think, a very interesting thing. Phi variables are, in a way, an awkward way to reason about definitions, and that it makes more sense to actually treat phi variables as formal parameters, essentially, formal parameters of basic blocks. So your x coming into this program is passed as a parameter to the basic block. Then you branch on that. And then here, when you do this merge between basic block 1 and 2, your phi is actually the parameter. So you're either calling the block with one value as an argument, or with the other value. It's exactly the same semantics. But the notation is much nicer, I think, and I think for functional programmers it makes more sense. And then one question arises is, in a graph like this, and if we think about functional programming, we're all about, scope, right? It's one of our fundamental things. What values are actually in scope in a SSA program? So at BB3, for example, we have 4 values in the program, A0, V0, V1, and V3. So which ones are actually in scope there? Well, not V0, because not every path from the beginning of the program actually defines V0 at BB3, because you could go through just BB2. So scope is a flow property, essentially. The values that are in scope are the values which are defined on all paths from the beginning of the program to wherever to your scope point, essentially. And this define on all paths property is called dominates. Your definitions dominate uses, and this is the fundamental invariant of variable use and definition in SSA. So to compute scope, you have to compute a kind of lightweight flow analysis. Another refinement you can make on SSA is to notice that control instructions have to end a block, right? So you might as well just store them in a different slot on your blocks. So now your block is predecessors, successors, the arguments to the block, which are the 5 functions, the instructions, which define values or produce side effects, and then a control instruction, which ends your block, right? And these are the same ones that we had before. But then if you think about it like that, then you're actually repeating yourself. Like, what are the successors of the block? You look directly at the control instruction, and you know, right? That's the only way to get out of the block. And so you don't need to specify the successors on the block itself. And to the same extent, you don't actually need to specify the predecessors either. You can if you want to, but it is repeating yourself. You don't need to maintain this predecessor graph, because you could just invert the successor graph. And then you think about, can I actually simplify this a little bit further? Well, yes, I can. You think about blocks itself, like it's annoying to have to keep instructions in blocks, right? It leads optimizers to make local optimizations, like just look at this block, I have no control flow, let me think about just that because I can't be bothered to think about the whole program. And then if you think about an optimization which transforms one graph to another, then you're like mutating blocks all the time, and it's really kind of gross. This is a problem, and I'm going to get to the resolution in a minute. Let's see. And this leads you to the thought that actually basic blocks are redundant in a way. It's not necessary for a basic block to have any instructions in it. You can just give a basic block to each instruction and make each instruction a control instruction. So your graph is an array of blocks. Your block has arguments coming in, which are the 5 variables. This turns every variable into a 5 variable. And then an instruction at the end. And your instruction would be, go to label L with the value of this expression. So now you have expressions and not definitions, right? So you're always calling blocks with arguments. And then you think about, like, well, basic blocks as a way of representing, or arrays as a way of representing programs is kind of annoying. When you're doing optimizations, you're always adding or removing. You have to like completely clone the array and then populate it. I don't like it so much. Let's make them maps instead, and let's make them functional maps. This sounds a lot better, right? So a graph is now a map of a label of the block to the block itself. And this is CPS, right? This is precisely lambda calculus here, without a formal scope tree, right? If your graph is a map from label to cont is a block, and your cont is a tuple of arguments and the term that it contains, this is exactly lambda, right? Tuple means lambda, arg means formal arguments, term is the body of the trivial body of the lambda, and your term can be like continue to L with the values from this expression, which is exactly calling a continuation with values, with any number of values, or branch or what have you. So when people say SSA is CPS or CPS is SSA, this is precisely what they mean. Like they are mutually expressible in this way for first order CPS. And the difference is, the only difference, is that there is no, in this representation of programs compared to classic CPS, there's no explicit scope tree. When you go to ask what's in scope at this term or at this cont, then you have to do a flow problem. You can't just like look up in the bindings, as you will. And this is the middle end IR in Guile. We represent programs exactly this way and have done so since, I don't know, it's like 2017 maybe or so. So you have conts that look like this. We have our formal variables and the term. We also have the source names they correspond to. You might like continue to a cont with the values from an expression with a source location. The expressions are exactly constancy. Like this is how we, this is the language that we use to bridge from the AST down to the lower level. And these are, the labels are small integers, and the values also are small integers in disjoint spaces. So same integer could refer to one or the other, but they're used in different ways. And the compilation unit is an int map from integers to terms. And these are all the different kinds of terms. Continue to a cont with an expression. There's also, any way you might need to use like multiple continuations, multiple branches, then you have a different kind of term. And there are 5 kinds of term in Guile. Terms that don't continue at all, terms that branch, terms that do it like a table switch, terms that impose a limit continuation, which have a handler continuation, and then different kinds of expressions. Okay. I'm going to kind of skip over a little bit of this. Within the first order graph, you can effectively do register allocation, right, on these locations, right? So effectively, the calling convention between every cont is custom and produced by the compiler, in the same way that register allocation produces a custom register allocation between blocks. But then when you get to separately compiled functions, then you need a common calling convention to join between them, unless you specifically know the type of the callee. And there are some specific conts to allow for taking positional arguments and returning positional values and things like this. So CPS soup in Guile is what bridges the AST and the low-level code. And it itself has 2 levels. When you first lower into CPS soup, which is essentially the very same CPS conversion, first-order CPS conversion as many people have done, then the scope, spans functions. The set of addressable values is the set of values that are in scope when the function appears in the source code, in addition to the set of variables that flow within that first order flow graph. And then there's a dividing line in the middle of the compiler that does the optimizing closures in O0 time paper that specifies closure representation. And at that point, free variables are referenced through the closure, right? So we get to do high-level optimizations that don't have to worry about where values are, and then low-level optimizations that are just within a function. And there are optimizations on all levels. Some can be on high or low. Some are just for high. And that's how it works. On a sort of practicality level, these int maps and int sets are closure-like data structures, or Bagwell-like, in the sense that they are functional maps. They share state. Adding to them is log n. And so your program is an int map from label to cont. And if you go to write an optimization, then you write a function, right? You write a function from program to program, which is really nice. And if you go to do an analysis, it's like a function from program to whatever you define your analysis in. So for example, if you go to identify what functions are in this graph, then you start with a program and a start label, and then you produce like an int set of labels that identify reachable functions in that graph. You can represent edges as int maps, compute successors in the same way. And so just as an example, if you're going to do flow analysis, like first order flow analysis, like the Fran-Allen stuff, right? Then you have a fixed point to perform, which is a mean over all paths of like the standard fixed point equation, right? And you can define this directly and functionally in CPS soup. So let's say we're going to compute available values in any given label. So not just values that are in scope, but values that haven't been killed by side effects, right? Values, this is the input to a CSE, common sub-expression elimination pass. Then we can represent available values as an int map of label to the set of values that are there. And then in the flow equation, your meet operation is just doing an int map intersect. And then when you meet the two sort of leaves of the tree, you do an inset intersect. And then to add values to the map, you do inset union. And to subtract, you do inset subtract. And then you have the kill and the gen sets, which is the standard flow analysis. At each point, which values are invalidated by that cont, and which are defined by that cont. And those are just insets itself. And the naive implementation would be quadratic, but because you have space sharing, and pretty sure about this, it's n log n, essentially, assuming that the number of values defined by a cont is, on average, like 1 value per cont. In reality, it's like 1 to 5 or so. So we get okay performance. And the good thing is that Guile is a very under-resourced project. And it allows like our few resources to not have to think about many things, to just have to focus on the problem. You can be a bit more efficient if you're directly mutating graphs. If you can reduce the cardinality of the graph by having basic blocks, which is what basic blocks do for you. But if you just want to think about the problem, like it's really nice to be able to do functional programming. And then I don't have to worry about a whole set of bugs, like the sort of mutating graphs in place, that kind of bug. And we get to apply the SSA optimization literature directly, right? Which is not the case for like ANF or something like this. You do have to do more pointer chasing. There's less like direct referencing of values. There's fewer arrays. There's more trees and such. It does, like SSA, it linearizes control in ways that maybe you don't necessarily want to. Like maybe you want to make a sea of nodes graph with control edges and effect edges or something. And then you end up recomputing things a lot. So it's not like the lightest weight of IRs, but it works for us, and it's an okay point. So in summary, CPS soup is Guile's IR. It's SSA, but distilled in a way that works for us. Labels and variables are small integers. Programs map integers to conts. Conts are the smallest labelable unit of code, and they have terms, or can have terms, that continue to other conts. That's the IR. Hey, did y'all enjoy that? We're back. We're back to WebAssembly. So the middle end is essentially all in Guile. And I have in parentheses like where these things come from. So we lower to CPS soup. We do the usual set of optimizations. We get down to the bottom. It's kind of the standard compiler pipeline at this point, with some knowledge of what scheme is, essentially. And then we get to the back end. And this is where we have the more Hoot-specific things. We do the true CPS conversion, the interprocedural CPS conversion, which, for historical reasons, we call tailification. And then you compute the dominator tree for each function. And then you apply this beyond relooper algorithm that Norman Ramsey and other folks presented a couple of years ago at ICFP. And this allows you to go from the kind of CFG representation of control flow and data flow to Wasm's structured control flow, these weird blocks and ifs and things. And then we directly emit for each cont some CPS code. We have a suboptimality in the sense that CPS soup is all about names, right? All the operands are names and all the definitions are names. And in our output of Wasm, we end up declaring a Wasm local for every name, which is suboptimal, and we need to do a binary pass on the end to kind of recreate stack data flow in the Wasm sense. And that will reduce the size of our programs. But that's a detail. And so at the very back of the back end, how do we get the Wasm out? Well, we have a full Wasm toolchain. This is the fun thing. Like we have a parser and a serializer for text format, and parser and a serializer for the binary format, and a linker that will pull in definitions from a standard library, and a standard library written in WAT, which compiles down to Wasm, so you can link together two modules. We have a number of transformations that we have on modules. For example, we emit Wasm that uses some experimental Wasm standards that are not in browsers, and we have post passes to reduce those away. You can polyfill them if you use the JavaScript term. We have a validator on the output, and we actually have a full virtual machine as well, which we use for testing. And All this has been really useful for us in the period in which Wasm GC was not standard, but it's also necessary for us right now because we use some Wasm GC features which are not supported by, for example, the WasmOpt toolchain that, for example, Jerome gets to use. Like the WasmOF ML toolchain gets to use a lot of upstream optimizations that's in this Binarian project, and we can't do that right now because Binarian does not accept our programs because we use multiple values in some ways that are completely in the standard and supported by the browsers, but not by the toolchain. And the result is not browser specific. It needs a little runtime for bridging calling conventions, for example, and providing access to host facilities. But we can run the same binary in Guile's VM, or in the browser, or in Node. And so where are we now? We have full R7RS, with the exception that we can't dynamically look up, dynamically create environments on the target side because of this tree shaking discipline. We will be able to at some point, optionally. We want to focus on being able to deliver small binaries, and small in our case is on the order of 100 kilobytes or so, or maybe a megabyte if you include a lot of stuff, like on that size. We have partial support for R6RS. Oh, we also don't have a working macro expander on the target yet. So all the macros are expanded on the host, and we don't have a macro expander compiled that works on the target, which is essentially the same consideration as not being able to have the interactive environment procedure on the target. We have partial support for R6RS. We have the module syntax and some of the modules, and probably will define all the rest. Partial support for Guile at this point. We have the module syntax, some module shims, some programs work directly, but it's still early days, right? We're still building this out. So in summary, it's a work in progress, but it's pretty good. There's a great release note. Yesterday there was a release of 050. Oh, we have one more cool thing, which is we have a fibers port, which lets you run green threads on the browser that integrates well with promises, which can stream results from HTTP fetch, and suspending the fiber when the fetch has no more data, and then resuming it when it gets more data, that sort of thing. Async iteration. So yeah, go check out the release page if you want to see a bit more details. And with that, I managed to nail it within the hour. The summary is that with the GC proposal and tail calls, which are almost ubiquitous, right, and going to be, then Wasm is a suitable substrate for us. It's not perfect. It can get better over time, and we should help it get better over time, but it's enough. And Hoot is a proof of concept here. There are other strategies you can take to compiling Scheme, even including these same features. I'm happy to talk about some of them. But for the Hoot context, like what we are aiming for in the next, I don't know, 3-4 months or so, is supporting all of Guile, all the Guile language, so that users can have the same program that runs in a normal Guile environment or on the web browser, and possibly merging into Guile upstream at some point, so that given a Guile installation, you can produce WebAssembly directly. And then as a call to action, schemers, y'all should steal the WebAssembly parsing backend, right? If you go to do WebAssembly experiments with Scheme, then you should consider stealing the code that deals with all the binary mangling, right? It'll get you somewhere pretty fast. And let us give Scheme to all the places, not just the servers, not just the users and computers, but like in the browsers as well. Thank you very much. Now I'll take questions. I want to learn.
So the question I was going to ask if you said yes was that your compiler pipeline approaches the structure of the transformational compiler, right? Which also did CPS and then did as for something pretty early, and then did optimizations on the CPS, and then lowered the CPS progressively further towards the target architecture.
Was this the one that ended up representing registers as formals in the back end of the
That's one way
compiler?
to do it, yeah.
Yeah.
I mean, it's very flexible. So, I mean, this lives on as the pre-scheme compiler
Yeah.
in Scheme. So it's part of the pre-scheme compiler that ships with Scheme48. And this observation that it's a pretty good idea to lower the CPS was also made ICFP 2007, something like that, where, I mean, there was kind of a phase where ANF was like the big thing, and then kind of CPS was rediscovered in a couple works. And so, I mean, it's only a handful of data points, but they all seem to be converging. So I'm afraid my question I'll turn into a comment.
But you know, I can build onto it on another comment, though, which is that I think the innovation, such as it is, of CPS soup is to not have a scope tree. And the reason why you don't want a scope tree is that you want to perform graph transformations that preserve the availability of, like, the definitions dominate uses property, right? But which might be invalid as algebraic transformations on a scope tree. Because the scope tree is not necessarily a dominator tree, right?
Yes.
In the scope, definitions must dominate uses, but it's not all dominating definitions are within scope, if that makes sense. And so I found in an earlier version of the CPS lowering that to do, for example, robust common subexpression elimination, I needed to take my scoped program, blow it up into an unscoped program, perform my graph transformation, recompute the dominator tree, and then reproduce a nested scope expression. And all, like, those 3 or so things on the side were steps I didn't feel like I needed, you know? So I felt like the lack of a scope tree gave me some freedom in performing graph transformations.
So it's been a while since I worked on that compiler, but I believe that exact thing is in there also.
Oh, good.
So it's probably, the solution probably looks a little bit different. I don't think it gives up on the scope tree, but it certainly allows you to do that sort of blowing up and reassembly and recomputing the dominator. So this is, so I guess what I was then going to comment after the answer to my question was that this is all indication that you're on a very right track. So.
As a kind turn to the end of the comment.
Okay, any other questions?
So I'm just curious if you have any benchmarks?
So we do have some, the R7RS benchmarks, right? And there are some places where the resulting code beats Guile, and there are many more places where it does not. And I don't have the benchmarks in front of me, and it's mostly related to the implementation of the runtime and strings. And so we have some overhead when we want to work with strings in WebAssembly with Guile's current, with Hoot's current compilation model. So I would say overall slower than native Guile, but occasionally faster if like a loop happens to end up, you know, in the right place with unboxed variables and everything like that.
So I had a question, which was in compiling to WebAssembly, right? It wasn't really designed to be a target for dynamic languages like Scheme, and so both, yeah, for performance maybe, what kind of features would you like to see in WebAssembly that would have made it a lot easier?
Well, I think I would like to see effect handlers, which is coming. I would like to see varargs. I would like to see, well, I mean, if I'm asking, I would like to have a native string data type, right? That would be obvious. A native bignum data type, that would be great. But at the least, the ability to add I32 values and branch on overflow, right? So the sort of like standard tricks you would get when implementing arithmetic. There's a lot more optimization work that I need to do on the emitted code. So it's not like all of the problem is in WebAssembly's WebAssembly's camp, but I think with those I would go quite a long way. Yeah.
Any last questions? Yeah.
So I was interested to hear that WebAssembly has this algebraic effects proposal Have you looked into it? Do you think it will be sufficient to just get you everything you need for delimited continuations as you use them in Guile? That's something that I'm, yeah.
I've looked into it a little bit. It is essentially delimited continuations, single shot, but nobody uses multi-shot delimited continuations. So I'm actually okay with like nerfing that feature, you know? It doesn't give anything to any user. My problem with it is that it uses the stack directly, and so I need to get a Stack Overflow solution that allows me to expand the stack. And if I get that and effect handlers, then that would be great. You know, that would be great.
Okay, and I have a very scheme-ish question.
Yeah.
Which is, I read this paper one time. It was called Lambda the Ultimate Go-To.
Yeah.
And I see now that WebAssembly does have tail calls built in.
Yeah.
So why do you need to do relooper still at the end? Why can't you compile over jumps to tail calls?
Ooh, that's a very good question. I mean, you don't, right? The implementations, it used to be that the model was, we're going to be super predictable. We're going to compile each function on its own, and that's just how it is. But now, V8 and other implementations are starting to do speculative inlining or inlining of functions they consider to be small, because the optimization is really give a small binary to the user, which kind of often goes against inlining in some ways. And so tool chains will ship binaries that don't inline things that they should for performance, and so the VMs start inline, which makes that sort of thing more possible. However, all of the implementations in browsers, at least, are really optimized for not spending too much time on things. And so what they would want to do is they would want to take like this set of minimal lambdas that you've got and actually understand their control flow graph and turn things into loops, right? Think about loops, and they don't have time for that. And nobody else is emitting code like that. So you should be emitting code that's a bit more conventional somehow to take advantage of the performance.
Okay, let's thank Andy.